We experience time as a linear progression, always moving forward, from the past through the present and into the future. This unidirectional flow is often referred to as time's arrow. Classical physics, particularly the second law of thermodynamics, reinforces this view. The second law states that entropy, a measure of disorder in a system, always increases over time. Imagine a cup of hot coffee left on a table. The heat from the coffee will dissipate into the surrounding air, eventually reaching equilibrium. The coffee cools down, and the room warms up slightly. This process is irreversible in our everyday experience. We never observe the heat spontaneously flowing back into the coffee, causing it to warm up while the room cools down. This increase in entropy, the tendency for systems to move from order to disorder, seems to dictate the arrow of time. Broken eggs don't unbreak, spilled milk doesn't spontaneously return to the glass, and we remember the past, not the future. This is the classical view of time, unidirectional and inexorably linked to the increase of entropy. However, the quantum world offers a dramatically different perspective. Quantum mechanics, the physics governing the microscopic world, presents a curious challenge to the classical understanding of time's arrow. In the quantum realm, the fundamental laws of physics are time reversal symmetric. This means that if we were to play a film of quantum interactions in reverse, the reversed events would still obey the laws of physics. Imagine a game of billiards on a quantum scale. Two particles collide, changing their trajectories. If we were to reverse the film, the particles would retrace their paths perfectly, ultimately returning to their initial states. This symmetry in the microscopic world creates a puzzle. If the fundamental laws of physics don't distinguish between past and future, why do we experience time as flowing in one direction? This discrepancy between the time reversal symmetry of quantum mechanics and the unidirectional arrow of time we experience is a fundamental question in modern physics. It suggests that our everyday experience of time might be an emergent property, arising from more fundamental time-symmetric laws at the quantum level. Recent research, such as a groundbreaking study from the University of Surrey, is starting to shed light on this intriguing possibility. In a groundbreaking study, researchers at the University of Surrey have provided evidence suggesting the possibility of bidirectional time flow in quantum systems. This research, published in a prestigious scientific journal, explored the behavior of a specific type of quantum system. They observed that under specific conditions, the system could evolve in a way that seemed to violate the typical forward flow of time. While the study did not involve sending information or particles back in time, it provided strong evidence that the arrow of time, at least at the quantum level, may not be as fixed as we perceive. The researchers emphasized that this finding has profound implications for our understanding of time itself. It suggests that time, at its most fundamental level, may not be a smooth, unidirectional flow, but rather a more complex and potentially malleable phenomenon. The possibility of bidirectional time flow in quantum systems has profound implications for our understanding of thermodynamics, particularly the second law. If time can indeed flow in both directions at the quantum level, it challenges the traditional view of entropy as always increasing. Imagine a scenario where a system could spontaneously decrease its entropy, becoming more ordered over time. This would be akin to the cup of coffee absorbing heat from the surrounding air, becoming hotter while the room cools down. While this seems impossible in our everyday experience, the University of Surrey study suggests that such processes might be permissible at the quantum level. This opens up fascinating possibilities for the future of physics. Could we harness these quantum fluctuations in time to create new technologies? Could we manipulate entropy in ways previously thought impossible? These questions are at the forefront of ongoing research, pushing the boundaries of our understanding of time and its relationship to the universe we inhabit. Time, an entangled illusion. The concept of bidirectional time flow also raises the intriguing possibility that time itself might be an emergent property. One leading theory suggests that time emerges from the complex interplay of quantum entanglement, a strange phenomenon where two or more quantum particles become interconnected and share the same fate, regardless of distance. Imagine two entangled particles, each existing in a superposition of states, meaning they occupy multiple states simultaneously. As these particles interact with their environment, their entanglement creates a kind of memory of their past interactions. This network of entangled relationships, constantly evolving and expanding, could give rise to the phenomenon we perceive as time. In this view, time is not a fundamental property of the universe, but rather an emergent construct arising from the complex interplay of quantum phenomena. This perspective challenges our intuitive understanding of time as a fundamental aspect of reality, suggesting it might be a more malleable and less absolute aspect of the universe than we previously believed. The challenge of proof-catching time in a bottle. While the theoretical implications of bidirectional time flow are profound, experimentally verifying its existence presents a significant challenge. The very nature of time makes it difficult to capture and analyze. Unlike other physical quantities like mass or energy, which we can measure directly, time is an experience, a flow. One of the main challenges lies in isolating quantum systems from their environment. Any interaction with the external world can disrupt the delicate quantum coherence required to observe time reversal phenomena. Furthermore, developing experimental setups sensitive enough to detect these subtle fluctuations in time requires cutting-edge technology and innovative approaches. Despite these challenges, physicists are actively pursuing various avenues of research. Some are exploring the use of ultra-cold atomic systems where quantum effects are more pronounced and easier to control. Others are investigating the potential of using photons, particles of light, to probe the boundaries of time. The quest to experimentally verify bidirectional time flow is a daunting but exciting frontier in modern physics. The philosophy of two-way time, free will and paradox. The potential for bidirectional time flow also raises profound philosophical questions. If the future can influence the past, what does this mean for our understanding of causality? Does it undermine the very notion of cause and effect, throwing our understanding of the universe into disarray? Furthermore, the concept of bidirectional time challenges our intuitive understanding of free will. If the future can influence the past, are our choices predetermined? Does free will become an illusion in a universe where the arrow of time is not absolute? These questions are not just thought experiments for theoretical physicists. They cut to the core of our understanding of ourselves and our place in the cosmos. Exploring these philosophical implications alongside the scientific research into bidirectional time flow is crucial for developing a comprehensive understanding of this mind-boggling concept. Time's mysteries, a journey without end. The quest to unravel the mysteries of time is a journey without a predetermined destination. As we delve deeper into the quantum realm, we are discovering that time is not the simple linear progression we once perceived. It is a multifaceted phenomenon, intricately woven into the very fabric of reality. The possibility of bidirectional time flow challenges our fundamental understanding of the universe. It compels us to rethink our assumptions about cause and effect, free will, and the nature of reality itself. While experimental verification remains a significant hurdle, the journey of exploration is no less profound. The quest to understand time is an ongoing adventure, a testament to the boundless curiosity of the human spirit. As we continue to probe the boundaries of knowledge, we can be certain that time, in all its enigmatic complexity, will continue to captivate and inspire us for generations